Okay, never mind. Let me try again. This paper, Unsupervised Feature Learning via non-parametric instance discrimination, is published in CVPR 2018. This paper is really hard for me. It's especially one step. It's really difficult. So I got stuck. At that step for several rounds. Okay, this paper is from UC Berkeley, Chinese Hong Kong, Chinese University of Hong Kong, and Amazon. Background: this paper is about non-parametric discrimination, so we need review the parametric classifier. First, we know the CN, the deep neural network, can do the classification task as with the supervised learning with a large number of label data. But now we should treat it in another way. We treat it as a treat the CN as a feature extractor. So we can see this diagram. Given an X, given a data X, we go through the convolutional feature learning and extract the feature V. The V equal to Fx is a n-dimensional vector. Here we give the example of the PyTorch data. Here the V is extract the data, then is flat this vector through flat is through a vector, and we have the V here, and then go through another fully connected layer. Now it's a linear classifier. Here we can see the FC here. So since we use this linear classifier, it's a parametric way. It's used because it's a parametric way, because it uses the layer. This layer, it have the W. It contains a huge amount of parameters or weights, and it's related to it's need to know the number of classes. So for this for this layer, it's a matrix. Basically, for each Wj, each row, it has the same dimension n equal to v. So then we can compute this one. It needs to have the same dimension, and in total, the W should have n m classes. So it's m times n matrix, and here this term or this operation, it's based on this one Wj is in production. It measures the similarity between the V and the J's category, because the Wj or the W, J, and N, it's the representation. It's a vector represents the J's category. So here, this one is the similarity. It's the inner product. We know it's equal to A times B times cosine A and B. So we use this one, the X, the V. We go through the FC, and the output is the logits. Okay, since we get the logits, the B goes to logits, and it goes to softmax. Here, this one is the parts of the logics and go through the softmax to compute the probability vector. Given the V, we want to compute the probability. It corresponds to the category I. So we have several classes, N classes, M classes, to get the probability vector and compute the cross entropy loss, and use backpropagation to compute the gradient, and use the gradient to do the SGD, stochastic gradient descent, to learn the W and also the CNN, the backbone. So it's a parametric softmax based on the W. But since we need the cross entropy loss, it requires large number of data, large number of labeled data. So in this paper they need to consider how to remove those labels. We don't want to use any labels. What can we do? So this is the motivation. Remove the labels. So without the cross entropy loss, we don't, and without remove labels, so we should not know the number of classes. We should not use the classifier. Then we can mainly focus on the feature extraction, this part, because now we have less information. So we focus on the backbone task. Now since we don't have this classifier, the fully connected layer classifier, we don't have the WJ. We don't have the W. Previously, we know the J is we can think it in this way. It's a supervision. It's a supervised signal to attract V. For example, this is a W cat. This is a W dog, and the XI is for example, it's cat 1. So we know the label. This is the label. We have the label. So this one will attract the VXI to the W cat. We want the distance or the similarity distance to be small, or the similarity to be large. But now we don't have label. We don't know the category. We don't know the ground truth. We cannot attract the V to the place, but we still need to find a loss, right? We still need a loss to give the V a destination. So this is a basic definition, basic step. We need to think some ideas, some alternatives to replace the WJ. They also talk about their motivation. Their motivation is based on the feature similarity, which means even they use the supervised learning, they also have the V, and FCV to get logics. So they also have the V. So basically, we can see if they have similar, the V is come from similar animals. They should have similar V. For the cat 1 should be similar to cat 2, and cat 1 should less similar to dog 1, and the cat 1 should almost not similar to like a house or something. So this is the basic idea. Then people believe, the authors believe, we don't need the labels. It should the neural network should know how to distinguish those features directly based on their based on the images, based on the instance. So different from the supervised way to attract the V, now we only have data, we only have instances. So we need consider another way to add an alternative to attract. So we use the push. We have it means we have several points. We have several points at the initial. It will learn some point, learn some hidden states at randomly, almost randomly, because the neural network will be initialized randomly. It will have some random points. Then we want to push those points between them, push them away between them. So which means if it's, for example, this is a cat 1, but we don't have the label, and we have cat 2, we have cat 3, and we have dog 1, we have maybe this is a house 1. So if we use this way, use the push, of course, it's very easy to push the house far away from the cat 1, and although we also give the push force on the category on the cat 2 and cat 3 and dog 1, but the distance, the similarity will certainly be different based on their own features, based on their images, and the convolutional layer a convolutional neural network can learn those features and push them away, push the unsimilar images far away. So this is the motivation, the intuition. Okay, so based on the idea, they measure the non-parametric similarity between instances, and we believe it can use this one to push different instances away and to distinguish those instances, although we don't know the labels for them. So let's expand it a bit. Now here the n is different. Previously we have n classes. Now it's n samples. So given a v, and we need to compare n samples, it's v1 to vn, so it compares to all of them. It's represent, given the v, the probability correspond to the sample I, and they have the similar method to measure the they use this in the product to measure similarity and use this temperature factor or hyperparameter, and it's also we can also treat it as the logits and go through the softmax to compute the probability vector and update based on the probability. So Yeah, so let's explain it more. Here the I is from I to M, so it tracks the I. Xi, the image, the data is Xi, and it gets the V, and of course, Xi should be itself, I should be I, and so which means the I, here we have n images, V1 to Vn. Here it should compare to itself. Of course, the probability should be as large as possible, and it should be different, push away from all other instances. This is the basic idea to compute this term. Okay, then they think because now the n may be large. For example, we have 50K, 50,000 images. Maybe we can compare with them, but it will be really difficult to compute, or it's very expensive to compute all of them for at every iteration, because certainly, of course, we don't want to update the V for every iteration for all V. So they use the memory bank. Use the memory bank. For example, we have n. We store all the V for the first time. Store them in the memory bank. Then, because we know for each iteration we have a batch of data, a batch size of data. So then we get a new batch. We just need it represent a subset, maybe not sequential, but some random instance in the memory bank. We select them and update them. It just update a small subset. So they use the memory bank to update less images, update less instances for each iteration. But it's still a problem for this formula, from this definition, because the n is still very large. We still need to compute this between each instance. Although we can use memory bank to update the V, to less update the V, but each time we still need to compute the similarity between those. That's still time consuming. So they use an approximation for the large n case. But why we need the large n for this unsupervised feature learning? Because we know in supervised learning, the n can be 10 or 1,000 ImageNet, 10 for CVPR 10. But why not now we need a large n? Because, for example, we use the ImageNet dataset, and our batch size, if we use 200, it's just like we have a V here, and we select 200 images. Maybe they are all select from other category, and it cannot conclude, it cannot cover all the category, and it's just a subset. Then the push force will be not accurate, and the most accurate force should be like this. We should have much more data from all category and from the category of itself. Then we have much more. We need much larger n to compute the loss. So it's not applicable. So they use the noise contrastive estimation (NCE) to cast the multiclass task to the binary classification. We consider it's only the data samples or noise samples if it's from the same data. From the xi itself is the data sample, and the maybe the from the same category. We can say it's the it's also from the data sample, but basically it just consider itself as the data sample, and the other images as the noise are the noise samples. So based on this noise NCE, the target is to compute the posterior probability of the sample I with feature V being from the data distribution. It's given I and V, the probability of if it's the from the distribution, the D equal to 1. If D equal to 0, then it means it's from the noise. It's from the noise sample, noise distribution. So the problem is how to compute this one. I can do some derivation for some step. It's equal to this one divided by this one. It's based on the conditional probability. Then use the Bayesian rules. It's equal to I V D equal to 1, P D equal to 1, and this one plus D equal to 0 times D equal to 0. And finally, they, in fact, in this paper, they directly give the definition, give an definition based on this one, equal to 1 plus n p n I. So from this to this, yeah, I can't find the way from this one to the final to their definition, but I can only explain it a bit. Here, this one is means it's a uniform distribution. We have n samples, n noise samples. So the probability to select one from them is n is 1n. 1n. And from the images, from the data, we believe the data sample is 1 versus n. If we have one data sample, it should have n noise samples. But in this paper, in the original paper, it's half and half, so it's a bit different. And also, I cannot make a connection between these two. So this is the difficult step for me. It's very difficult for me. Okay, so we have for each images we have this distribution, uniform distribution from the noise sample, and we know it's 1 versus n, and we select one images. The probability belongs to I is this one, and we select and we have a very high probability. It's from the noise samples. So it's a very, I think it's not an accurate explanation, but just some intuition about this one. Maybe we just need to consider as a conclusion. Okay, so based on previous result, we have this one, and then because the z is also based on the n, so now they think they will use a much less number m to replace the value. So they computed the z equal to this term. So it's from n to m. So finally, the noise contrastive estimation. Noise, the loss is this term. It's if it's the data sample from the data distribution, it computes this probability. If it's from another noise contribution, noise distribution, it's v prime. It's another images. Then it should belongs to. It should not belongs to the the sample I. So it's use 1 subtract the HIV prime. The I prime is, it should not be the ith sample. And we compute the expectation with the m. We have m, the data sample is 1. The noise samples are m times more frequent than the data sample. So this is the noise contrastive estimation. I think the derivation is a bit complex. It should be an approximation. So this paper, in fact, is harder than following papers, because big companies say they love larger n. They directly optimize on larger n. We will see those papers soon, and they also consider different factors for optimize. Next, they consider another thing is the proximal regularization. It's also about the update in the memory bank, because we know the network. We will update the network after each iteration. We use the step. We update the use the gradient to update the network. So at the early phase, it may have some. The learning is the oscillating. The network will change dramatically, and the V in the memory bank will also be changed dramatically. So it's not a good behavior. So they requires they want the change to be small from the iteration t subtract 1 to iteration t. So they just need to add this proximal regularization with the coefficient to let the change to be small. Here, this one is the distance. So they want the change from time step t subtract 1 to time step t to be small. So this is then they plug into the formula and get a new formula with the proximal regularization. The first component, they give a weighted k nearest neighbor classifier. First, we have you apply the unsupervised feature learning to learn the CNN, the extractor. Then to classify text images, x prime, x hat, we extract the hat. In fact, it's this one. Then compare it with all images with the cosine similarity. So this is the f hat compared with all feature in the memory bank, and then select the top k nearest neighbors and compute the w, the weight for each class. The class, for example, if it is cipher10, it's 0 to 9. So for each class, they compare the k nearest neighbors. We select the neighbors one by one and check their category. If the category is this category, it gives 1. It's the indicator function, and times the similarity. It's like the weight. Yeah, it's the weight. So finally, this one I think it's the weight is also a n classes vector. And finally, for the real classifier, I think is just select the max, select the max value, the index of the max value. So this is about the KNN, the weighted KNN. Okay, the results. Here, this one is the KNN, and this is the feature after this layer, and use the feature after this layer to go through a linear SVM with labels, I think, to compute the classification accuracy, and it shows their method is much better, outperform previous method. And finally, I don't want to talk too much about the results. So let's go to the summary. The paper come up with an approach for the unsupervised feature learning, and next many works are based on this paper, like Moko, Sinclair. So, and they give it a new domain, new direction. It's contrastive learning, based on the idea of this method. Because why it's contrastive? Because compare with other instances, so it's contrastive. So first, it's the V, given an image to extract the V, and it compare with n instances to measure the probability correspond to the I samples, and update based on this probability. Second, they apply the NCE with this term to this is an approximation for large n problem for that issue. And third, they use the proximal regularization. They want the update in the memory bank to be small between next step and a current step. So this is the summary of this paper. Thank you. I hope this is a difficult paper. Thank you.